So we're transitioning into chapter 10, the marine environment. And in doing so, I want to look at how the concentration of the major ions changes from the rivers to the oceans. We'll also look in this very short video about the budgeting of some of these elements within the ocean. And so in this example, we're going to look at one creek that's up in New Hampshire. It's the Hubbard Brook. And so the geology there is granite shield, very, very old and weathered environment. And we're going to look at how the constituents within the water changes as we go from rain to high elevation and down to low elevation. And so what I would expect from you is be able to look at these data and explain why we see the changes we do. And so again, we can look through here. Let's start with hydrogen ion or pH. We see that the pH does change. It does increase as we go from the top of the mountain down below. And as I mentioned in a previous video, that's most likely to the addition of buffers, things like carbonate, or even just organic acids, or potentially more photosynthesis, changing the system such that we increase our pH. We also see in terms of, say, aluminum, which maybe we wouldn't expect it, but it actually goes lower, and that's due to the increase in pH. Due to the increase in pH, aluminum actually drops out, much like iron did in a previous video. Other things such as calcium and sodium and, say, silicic acid, what we see in these cases is that they accumulate. They're more of an additive constituent as we continue to add more tributaries to the stream, and their concentration actually increases here. And then lastly, what we see is the nutrients. We actually see uptake of these nutrients, and maybe that's a good sign of photosynthesis is occurring, such that we get a drop in nitrate and we get a drop in ammonium ion. Just note that we are up in New England, and they do experience quite a bit of acid rain up there due to the industry that's in the upper Midwest. So now let's look at some of these elements and their concentrations within ocean water and river water. So let's do a quick comparison. With respect to the elements that I have listed here, in all cases, we see an increase in their concentration when we compare river water to ocean water. So the ocean contains much more of all of these ions than does the river water. And so when we look at the residence time of these elements within the ocean, we see that they spend a very long time in the ocean. And so we haven't talked much about elemental cycling of elements like these, but you should note that these elements have cycles that are on the scale of tens or hundreds of millions of years. And so we think of something like chloride. So we're talking 200 million years chloride on average spends in the ocean. And so you should be able to calculate oceanic residence times. That is nothing new to you. You know that all you'd have to do is take the amount of material that is in the reservoir, in the ocean, and divide by the flux, either the in or the out, to get the residence time. And so the reason, again, that these elements have such a long residence time within the ocean, we could say it's due to the fact that there's so much of these elements within the ocean. But really, what's actually happening here is that these elements have such a low flux. How they are able to get out of the ocean and back on land is a very slow process. So I've selected a few of these elements to talk about and look at how they can actually go from the ocean environment and back onto the continent. And so with respect to how they get to the ocean, it's primarily through river input. So we see these numbers with positives. This is how they get to the ocean. How they leave is with the negatives. And so in terms of the fluxes here, I have them in units of 10 to the 12 moles per year. The inventories is in 10 to the 18 moles. And so in terms of chloride, we look at just chloride, it enters the ocean through river input, but the only way in which it can get out of the ocean is through the atmosphere, through sea salt and sea spray going back onto the continent. But what we do see is that we have a balanced, steady state for this cycle. But again, because of the small flux relative to the large inventory, this cycle takes hundreds of millions of years. We have sodium, which also depends upon sea spray, but also through ion exchange with the sediments. These sediments sometimes get reburied, get subducted, and that is a part of the sodium cycle. Also, this category is interesting. This is the hydrothermal vent activity and how it contributes to the cycling of some of these elements. The one element that it really affects is magnesium. Magnesium is actually lost within the hydrothermal vents. When the seawater goes into these vents, the magnesium actually precipitates out, gets removed, and it helps balance the cycle. So again, if you look at any of these rows here, what we see is that we get a mass balance where what comes in must go out, and it does so such that the net is zero. And so we can look at these other elements as well. There are a couple other processes that affect these elements, such as calcium. One effect is carbonate deposition. So just the formation of calcium carbonate, maybe even the burial of calcium carbonate in terms of living organisms. And in terms of sulfur cycling, it depends upon the redox conditions, and such that if we get anoxic conditions, sulfate, for example, can be turned to sulfide, and that plays a role in balancing the sulfate um, concentrations within the oceans. So that's all I have for you with this video. I just wanted to introduce to you the idea of the differences between river and ocean concentrations, and also dive one last time into elemental cycling and the calculation of mean residence times.